Okay, so the second problem, I actually got looked up a centrifuge on Amazon.com. So a centrifuge, maybe you've used one in chemistry or in biology. They spin. You put these test tubes in it, and they spin. And as the test tubes spin, they produce what you might call artificial gravity, and it separates out the fluids. Okay, so if you got blood in there, all the heavy stuff in the blood, like the cells, they'll go to the bottom end, and the plasma, the fluidy part, will rise to the top. Or if you've got milk in there, it'll separate into the various layers of milk, with the heavier stuff, the denser stuff, going to the bottom, and the less dense going to the top. Okay, so centrifuges are used to separate colloidal solutions that way. Okay, so I looked this up, and all the numbers are real except for this 45 seconds. Okay, I just didn't know how long it takes to spin up, and I couldn't see that in the specifications. But we have a centrifuge, and it starts from rest. Okay, and it spins up to 5,000 RPM in 45 seconds. Okay, so you can imagine, you put the test tubes in there, you close it, and then you turn it on, and it starts spinning slower, and then faster, 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 faster. And then after 45 seconds, it's spun up to 5,000 RPM. Okay, and RPM stands for revolutions per minute. All right, the bottom of the test tubes, okay, because the test tubes are sitting in there, and then the opening is closer to the axis, to the axle around which it spins, and the bottom of the test tubes are the furthest. Okay, so the bottom of the test tube experiences an acceleration of 3074 g. Again, that's actually one of the specifications. Okay, that's a lot of acceleration, by the way. We'll see how much that is in a minute. So 3074 g, what does that mean? G here means acceleration due to gravity. Okay, so technically 9.8, but we'll round it off to 10 meters per second squared. Okay, so that's how much acceleration, an object at the bottom of those test tubes, that's how much it experiences, how much acceleration it experiences once this thing is spun up to 5,000 RPM. Okay, and then I just say assume constant acceleration, I guess, for the first 45 seconds. All right, so that's our situation, and then I ask some questions. The first question is, what's the angular acceleration? Okay, so what's angular acceleration mean? It means not how fast it's spinning, but how fast it's spinning up, the rate at which it spins up. So if it's spinning at 5,000 RPMs and it just stays at 5,000 RPMs, there's no angular acceleration. But if it starts from 0 and then it goes to 100, 200, 300, all the way up to 5,000, it's speeding up. Its angular velocity is increasing, and in that case, there's an angular acceleration. Okay, and this is spinning up, and so I asked for my first question, what is the angular acceleration? All right. Second question is, how many times does it actually turn during the first 45 seconds? Okay, so it starts at rest, and it's going to make one turn, two turns, three turns. Now, the time it takes to make a turn decreases, but you could still count how many times it's turned in that first 45 seconds, and I want to know that number. How many times is the centrifuge turned during during the first 45 seconds? Okay, as it spins up. The third question is, what's the centripetal acceleration at maximum speed? Okay, so once it's spun up, what's an object at the bottom of that test tube? What acceleration is it experiencing? Okay, and how far is the bottom of the test tube from the axis? Okay, so when something spins, it spins around an axis, like a door. When a door turns, not that it's really spinning, but it's still turning. There's a spin there, so I should say any kind of rotation. Any kind of rotation occurs around an axis. For a door, those are the hinges. Okay, there's an axis that passes through the 2 or 3 hinges that holds the door in place. Okay, with this object here, if I grab it at the end here like this, my 2 fingers are holding it in place, and then I turn it like that. Okay, and the axis around which it's turning is between my 2 fingers. Okay, so there's an axis, and the bottom of the test tubes are some distance from that axis, some radius from that axis. Find that distance. Okay. And I actually don't know the real number, because that wasn't part of the specified answer. But the answer that I got calculating it was pretty reasonable, and we'll see that in a second. Okay, and then finally, how fast is the point at the bottom of the test tube moving? Okay, I'm actually asking for the linear velocity or the tangential velocity. Okay, not how fast is it spinning, but like if I were to measure, like, how fast is it moving? How many meters per second is this thing moving at? Okay, as it moves. I know it's moving along a curve, but still, you could ask, how fast is it moving along that curve? Okay, so okay, there are the questions. Let's start. So to answer the angular acceleration question, it's probably best to start with the equations for angular kinematics. Okay, now angular kinematics assuming constant angular acceleration, constant alpha. Okay, so there's the first equation. There it is. Okay, and this is slightly different than the way I usually write it, but it's probably a better way to think about it. And the way I usually write this equation would be like this. It'd be like theta here is equal to that plus theta naught, like that. Okay. And what is this? Well, it says, look, if you start at some angle theta naught, some orientation theta naught measured by an angle, and you start with some initial angular velocity omega naught, and you have some angular acceleration alpha, and you wait a time t, then you're now at a new angle theta. So you start at this angle theta naught, and you wind up at this new angle theta, and this is the equation that gives it to you. Well, our initial angle, and that's not so interesting. Okay, that's kind of like tantamount to choosing an origin. So it's more interesting to look at the change in the angle. Okay, so if I subtract theta naught from both sides, I subtract theta naught from this side, then I lose my theta naught over there, and I get this equation. Okay, and then the next thing is like that's kind of ugly there to say theta minus theta naught. That's just your change in angle, like I wrote there. Okay, and so this I'm just going to replace with theta naught, and when I do, I get this one. Okay, so this is not different. I don't remember exactly how I did it in the pre-recorded lectures, but that's no different than the other way that I just wrote it. Okay, it's just this is a little bit better to think about because you're not thinking so much about like what orientation you're in, what angle. It's like what angle did you turn through, and that equation will give it to you. Okay, so here's the second equation, and that is like if you start off with some angular velocity omega naught, and you got an angular acceleration alpha, and you wait some time t, then you wind up at some other angular velocity omega. Okay, and then the third one is just these other two with the time eliminated between them. Okay, so let's go through it and see what we know. Let's read the problem again. A centrifuge starts from rest. Okay, so starting from rest means you're not turning. Not turning means your angular velocity is zero. Your initial angular velocity is zero. Symbolically, that is omega naught equals 0 radians. Okay? The second thing is how fast does it spin up to? Well, I say that it spins up to 5,000 RPM. Okay? So our omega, our final velocity, is 5,000 RPM. That's not an MKS. RPM is revolutions per minute, okay? And revolution is just turn. It's like how many turns does this thing do in a minute? It does 5,000 complete turns every minute, which is pretty fast, okay, if you think about it. So in 60 seconds, this thing is turned 5,000 times, okay? But we need it in radians per second, okay? So, because that's, all my equations only work if you're in radians and in seconds, okay? So, we need to convert the time. So minutes here is in the denominator, so we put it in the numerator in our conversion fraction. And 1 minute is equal to 60 seconds. Okay, so 1 minute divided by 60 seconds, that will eliminate the minutes there and give you seconds. Okay, and then revolution, you want to convert from revolutions to radians, and revolutions in the numerator here, so you put it in the denominator of the conversion fraction, and 1 revolution is 2 pi radians. Okay, and so that converts that to radians per second. Excuse me. So there you go. Now, just to know that you're in the right ballpark because you might make a mistake here or something, if you've got it in revolutions per minute, roughly dividing by 10 will give it to you in radians per second. Not exactly, but just roughly. Okay, so you expect the number to decrease by a factor of roughly 10. And if you take a look here, you went from 5,000 to 523.6. Okay, so I mean, like if you flip one of these fractions around, you'll get a totally wrong answer. So just as a check, yeah, this number should be roughly 1/10 of that number. Okay, great. We've got the final velocity in radians per second. How long does it take to spin up? well, 45 seconds, okay, and that's all you know, okay. So there you've got those. You look back at our equations here, and you go, which one can I use? And you can't use number one, and you can't use number three because you don't know alpha. That's what you're trying to find, and you don't know theta. You just don't know it, and so the only one you can use is number two. And so you start from equation number two there, like that. Substituting in omega is that, and so there it is. Alpha is what you're solving for. T is 45, omega naught is 0, and ta-da, you get an alpha of 11.6 radians per second squared. Okay, so there's our first question. All right, let me see if there's anything in the chat there. Okay, you guys are doing fine so far. Okay, so how many times does the centrifuge turn uh, during the startup time of 45 seconds? In other words, how many times does it turn during that first 45 seconds? Okay, now um, this question is a little bit, students can get a little bit confused over it, and that's because I'm asking how many times does it turn? And now you look at these equations up here and you go, well, which one is turning? I mean, like what variable corresponds to turn? And it's actually the angle. It's actually this angle here. And you go, well, I don't understand that. How is an angle turning? Okay, usually when you say angle, you think of like a wedge, and you think about that angle in there. But a turn is an angle, or an angle is a turn. Okay, an angle could be like a fraction of a turn. So, you know, if you say something like a quarter of a turn is 90 degrees. Half a turn is 180 degrees. Okay, a complete turn is 360 degrees. Okay, now I'm saying that in degrees because most people think of degrees better than radians. Okay, but you know, if I said an eighth of a turn is 45 degrees. Okay, so you can see that a turn and an angle really are the same thing. You say, well, what if I do two turns? Well, then that's going to be 2 times 365. What if I do 3 turns? Well, then that's 3 times 365. Well, what if I do 3.5 turns? Well, then that's 3 times 365 plus 180 for that half turn. And so you can see that the number of turns and the angle really are the same thing, okay? So, you know, like the language will sometimes trick you. You know, you'll get caught up in the language and you'll say, what is he asking for? Number of turns. I don't see number of turns as any one of the variables. It is. It's the angle, okay? So you could use either equation 1 or equation 3 here. Either one has delta theta in it, and that's what we're solving for. Okay, I chose number 1. I don't know, just because I guess delta theta is already isolated. All right, so there it is. And then substituting in, it's pretty trivial. We know alpha now. Now we know alpha, 11.6, so we substitute in for that. 45 seconds squared. There's no initial velocity, so that's 0. So that works out to 11,745 radians. Okay, now that is the answer, and you know my tests are multiple choice. So if you see that my answers are in radians, then you say, well, I got to match 11,745 radians. Okay, and hopefully one of the answers is that number. Okay, but suppose you look at my answers, and my answers are in turns. And after all, I did ask the question, how many turns? How many times does the centrifuge turn? Okay, so I'm kind of suggesting that I want the answer in turns. And you go, but I don't have the answer in turns. I have it in radians. Well, what do? Convert back. Okay, so here it is. Radians is in the numerator, so you want radians in the denominator, and then to form the fraction. Remember, this fraction has to equal 1. One revolution is 2 pi radians, and so 1 revolution divided by 2 pi radians, that's equal to 1, and you can always multiply by 1. So this whole thing is like multiplying by 1, but it's a cleverly crafted 1 such that the radians will disappear, will cancel out, and it'll be replaced by revolutions, and you get that it's 1,869.3 revolutions. Okay, so that's how many times this thing would turn in that first 45 seconds, which, if you think about it, is quite a lot. Okay, I mean, this thing is really spinning pretty fast. All right, okay, let's move on to the next question. The next one is, what is the centripetal acceleration at maximum speed? So if we go back to the problem, the way I worded it, you say, well, I mean, usually when students see a question like that, they'll go, well, what equation do I need? Okay, well, the answer is stated in the problem, the number is stated in the problem, but in a slightly cryptic fashion. So think about what I'm saying. Okay, so you know, when something is spinning, think of uniform circular motion. I know this isn't quite uniform circular motion, but it is after it finally spins up to 5,000. It starts off slow, 100, then 200, 300, 400, 500 RPM. It spins up to 5,000 RPM, and then it doesn't spin any faster. So it reaches the maximum, and then it spins at 5,000 RPM. Well, that 5,000 RPM, once you're up there at that rate, you don't spin any faster, and that means that you're at constant rate, a constant angular velocity. That is uniform circular motion. In uniform circular motion, there is an acceleration because even though the thing is moving at the same speed, it doesn't speed up or slow down, it has to turn. And any change in the velocity, whether in the magnitude or in the direction, is an acceleration. So there's going to be a turn. This thing's turning, 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 turning all the time. And as it turns, there's an acceleration towards the center. And that acceleration towards the center is what's causing the acceleration in those test tubes, which is causing the separation. And I tell you what that is, at least at the bottom of the test tube. The bottom of the test tube experiences an acceleration of 3,074 G. Okay? And so down here, when we solve this problem, what's the centripetal acceleration? That is this 3074 G. Okay, so there's G. But you needed an MKS, so what you do is you just take out G and multiply 3074 multiplied by G, and you get that the centripetal acceleration is 30,740 meters per second squared, which is huge. Okay, basically that is 3,000, like anything at the bottom of that test tube would weigh 3,000 times more than it weighs ordinarily. Okay, humans can barely handle like at 7G, like from 7 to 9G we faint. Okay, if you're in a fighter jet, maybe you can experience 7G for a few seconds, but if it continues too long, you'll actually faint. 3Gs on a really wild carnival ride or something like that, but you wouldn't enjoy it for very long. This is 3,000 Gs. Okay, so the acceleration that's experienced by the whatever bacteria, cells, or whatever are in that test tube, is going to be extreme. They'll get crushed. Okay, they're not going to be those poor bacteria are not going to be very happy campers in there. Okay, so there it is. There's the centripetal acceleration, and we give that the symbol AC. Okay, now actually when you have uniform circular motion, you only have centripetal acceleration. But when you actually have an angular acceleration, there's also a tangential. Not only is the velocity turning, but it's also speeding up. And so the turning gives rise to the centripetal acceleration. The speeding up gives rise to the tangential. But the centripetal acceleration is much, much bigger than the tangential. We'll see that in the last problem here. So in the last problem, it says, no, yeah, sorry, second to last problem. How far is the bottom of the test tube from the axis? Okay, you say, well, what's this got to do with acceleration? Well, there are two accelerations, like I just mentioned. There's the centripetal acceleration, and then there's the tangential. You say, well, which one do we want? That's the one that's going to be much bigger. We'll see that when I get R in just a second. That's the one you want because that's the one that's responsible for really causing that separation. The other one is small. Okay, so if we use this formula right here, there it is, and we isolate R because that's what we're trying to solve. AC, well, we just calculated that. That's that 30,740 meters per second squared. Okay, so there's your centripetal acceleration divided by the angular velocity squared. Okay, we got that angular velocity. That's when we converted the 5,000 RPM to radians per second. There it is. Okay, and if you work that out, that turns out to be 0.11213 meters. Okay, and if you convert it to centimeters, that's 11.2 centimeters. Okay, and that makes sense, doesn't it? Okay, 11.2 centimeters. I mean, if you gotten an answer which was like a meter, that doesn't make sense. Centrifuges are about this big. And the test tube's inside, there's the axis right there. The bottom of the test tube, it's about 10 centimeters from the axis, and we got 11.2. Now, I couldn't find that number in the specifications, but that makes sense. I mean, I've used them. Maybe some of you have used them, and so 11.2 centimeters, yeah, makes total sense. Okay, and that that angular velocity right there. at that radius right there, it gives you that 30,740 meters per second squared. Okay. Now, while the centrifuge is spinning up, there's also this tangential acceleration. Let's see how big that is. It's the formula for it is different. So for the centripetal, it's r omega squared. For the tangential, it's just r times omega. Well, r we now know is 0.11213, okay, in meters. The acceleration we found above, angular acceleration we found above, is 11.6 radians per second squared. And if you work that out, that turns out to be 1.3 meters per second squared. Well, compare that 1.3 to that 30,000. I mean, I think you'll agree that the centripetal totally swamps out the tangential. The tangential is absolutely negligible. It's there. If it weren't there, it would spin faster and faster and faster. So you need a little bit of a tangential acceleration to speed it up as it spins. But as it starts to spin, okay, faster and faster and faster, it's that centripetal acceleration that's really big and really doing all the work in a centrifuge of separating out the colloidal solution. Okay, so there we go. That's that question. And then the final question is, how fast is that point at the bottom of the test tube moving? Okay, and that's given by this formula here. Okay, the tangential velocity, that is, imagine that you're like a speck running along with the bottom of the test tube as it goes around. I mean, you're moving at some velocity. Okay, how fast are you moving? Even though you're turning, you've got some velocity, some linear velocity. And you say, how fast is that? And that tangential velocity is given by r times omega. And so r we have from the previous question, omega we have from above, and that turns out to be 58.7 meters per second. Okay, now how fast is that? Like, how fast is 60 meters per second? That's pretty fast. It turns out to be 211 kilometers per hour. And, over 200 kilometers per hour, that's probably going to be like 130 miles an hour. So this is moving very fast. And so as a safety feature, these centrifuges, they have a lid. You got to close the lid because you can imagine if it's spinning this fast, you put your finger in there, you're going to get really hurt. Okay, these things are spinning extremely fast. Okay, so there it is. That answers the last question. So here's question number 3. A rod of length 1.2 meters and mass 3 kilograms is free to rotate around its center. Okay, whoops, got that up too high. There we go. Okay, so a rod of 1.2 meters and mass 3 kilograms is free to rotate around its center. So I don't have a rod here, but if I take my remote here and I just like allow it to rotate through the middle, there we go. It's like free to rotate like that. That's the situation we have. I'll draw a picture as we work through the problem, but that's what we have. So with a rod, we consider two possibilities in the pre-recorded lectures. I talked about a rod rotating around the middle. The other one was a rod rotating around one of the endpoints. Okay, like this. Okay, so a rod rotating around one of the endpoints. Okay, but this one is rotating through the middle. Okay, it's initially at rest. Okay, and what we're going to do is we're going to apply a 100 Newton force 20 centimeters from the center at an angle of 45 degrees. So this one might be a little hard to picture right now what to do, but I'll draw a picture for that one. Okay, when we get there. Now, like with a lot of my problems, you might, if you think about, like, you just read them, you might anticipate where I'm going to go with what kind of questions I'm going to ask about these things. Okay, I mean, I remember doing this when I was a student. I would kind of know what kind of questions the professor was going to ask, because there's like not an infinity of all different possibilities. Okay, and yeah, and like, you don't want to throw something at the students where they're like, did we even study this in class? Okay, so if you look at this, you go, just what kind of a problem is this? And you can already see that this is going to be a tau is equal to I alpha problem. Okay, like the angular equivalent of Newton's second law, because we're applying a force and we're going to get it rotating. Okay, so as soon as you apply a force, that translates into a torque, and then it's going to start rotating. Okay, but now I'm walking you through it anyhow. So the first question I ask is, what's the moment of inertia? Okay, so the moment of inertia, I gave you quite a few different ways of calculating it. The first thing is it made up of point masses? Okay, if it's point masses, then for every mass, every point mass, you just do mr squared. You just mr squared for the first one, plus mr squared for the second one, plus mr squared for the third one, add them all up, and that's your moment of inertia, okay? But then I also gave you a moment of inertia for some special shapes like a rod, or a sphere, or a drum, or a disc. And actually the drum and the disc are the same, because if you take a drum and you squish it down, a disc is just a very thin drum, okay? And the height of the drum doesn't really matter. So it's the same formula for a drum and a disc, okay? So I gave you some formulas like that. And those are particularly important for people that are going into like PT or ESS, because sections of the human body can be modeled by those shapes, okay, like the arm here, it could be like a rod, okay, roughly speaking, okay. The forearm could be modeled as a rod rotating around one of the endpoints, okay. So that's why I gave you those, and there's quite a few of them. I just gave you a few to for the purposes of the course, but there's actually a wiki page that lists them all off, and there's quite a few of them. All right. So anyhow, I digressed a little bit, but I want the moment of inertia. So what you do is you say, well, which one of the formulas do I want? Well, this is a rod of uniform mass, so I want the rotating around the center, so I want the formula I is equal to 1/12 ml squared. Okay, so 1/12 ml squared. So just plug in the numbers, 1/12. The mass is 3. The length is 1.2. Okay, and you want to square that, and that gives you a moment of inertia of 0.36 kilogram meters squared. Okay, so there's the moment of inertia of your rod. All right, and then the next question is, what is the torque due to the force? Okay, so what is the torque due to the force that we're applying? Now for this one, before jumping in and answering questions, let me draw a picture so you have an understanding of what's going on here. Okay, so let me create a new whiteboard, and let me close this one, because I'm afraid that if I don't close this one, it's going to crash again. And 1 second here, let me close. Oh, okay, you know what? I didn't have to start another one. Let me close that one. Too many windows. Okay, there we go. Okay. Oh, it crashed. Jeez. I did all that so that it wouldn't crash, and of course it did crash. All right. When I started from fresh, it's okay. It's when it already has a diagram up, it decides to just crash. All right, there we go. I'm pretty sure this won't crash. So okay, let's start off. Here's my bar, like that. Okay. And the bar rotates around the middle. So here is an axis of rotation, like that. Okay, and it's going to be able to rotate. Let me do this in blue. It'll rotate like that, around that axis like that. Okay, the entire length of the bar is 1.2 meters. Like that. So half of the bar, like this, is going to be 0.6 meters, like that. Okay, but that's not even what's happening here. Let me just reread it. I'm going to apply a force, 100 Newton force, 20 centimeters from the center. So actually, I'm going to be applying a force. Let me do the force in, I don't know, green here. 20 centimeters. So zero point 0.6 is like 0.6 is like 60 centimeters, and so I'm just going to be applying it. It doesn't matter which side. I'm going to be applying it right there. Okay, where this distance in there now, that distance there. Whoops, I didn't draw that too good. Okay, that distance in there, that is going to be 20 centimeters or 0.2 meters. Okay. And how am I applying the force? I'm not applying the force perpendicular like that. Okay. I'm actually applying the force at 45 degrees. And it might be a bit ambiguous, because you might say 45 degrees this way or 45 degrees that way, and it actually doesn't matter. It's the same torque. So like that, where this angle in here, let me do it in red, that angle in there is 45 degrees, like that. And the force is 100 newtons. Okay. Now, you would get the most torque if you pushed out here at 90 degrees. Okay. Picture a door. When you go to open a door, the doorknob is put as far from the hinges as possible. So the hinges are like here. Okay. And you can't turn a door by pushing on the hinges. Rather, you want to push as far from the hinges as possible, like that. And you want to push perpendicular. Like you want to push at 90 degrees like that. Okay. So here, uh, we're less than ideal because we're pushing at 20 centimeters rather than more, and we're pushing at 45 degrees rather than 90 degrees, okay? So it's less than ideal, okay? And so I ask, well, okay, we'll calculate that torque. And so here's the formula. The torque is equal to RF sine theta. Yeah, a force gives rise to a torque, but the bigger R is, the more torque you get. And the closer the angle is to 90 degrees, the more torque you're going to get, okay? And that R, you say, how do I measure that R? That R is, in all of these problems, R is always measured from the point of interest to the center, to the axis, okay? So where's the axis? Let me do it in blue here. Let me just circle it. There's the axis right there, okay? And where's the point in question? Well, we're applying the force right there. And what's the distance between those two? 0.2 meters or 20 centimeters, okay? So, all right, so how do I plug in here into my formula? For R, I'm going to put 0.2 meters. For F, I'm going to put 100 newtons because I said it's 100 newtons force and not 20 centimeters. And the angle is 45 degrees. And so that turns out to be 14.14214 newton meters, okay? And why newton meters? Well, because I've got a newton there and a meter there, okay? So the units for torque are newton meters. By the way, just a bit of an aside, a newton meter is also a unit of work, which is a joule, okay? But no one ever writes joules for torques. I mean, it looks kind of weird, okay? And the reason is that everyone thinks about torques in terms of this formula, okay? It's R times F, okay? And then sine theta, of course, okay? But, usually people apply a torque at 90 degrees because that's obviously when you're going to get the most torque is when, R and F are perpendicular to one another. But, there still is an angle dependence. But, the bigger R is, the more torque you get. The bigger F is, the more torque you get. Okay, that's why, like a wrench, the longer the arm of a wrench, the easier it is to screw a bolt or unscrew a bolt. Okay, so you want to make R as big as possible because that gives you the biggest twisting action. Another way to think of torque is like a twisting or turning, the ability to turn something. Okay, so anyhow, that answers this question. The torque due to this force is 14.1 newtons. Okay, if I were to, on a test, of course, I would round this off to 14.1 newton meters. All right, next, what is the acceleration, or what is the angular acceleration? Okay, so what's the angular acceleration? Well, is there a relationship between tau I and alpha? And the answer is yes. It's tau is equal to I alpha. That's kind of the point of this question. And that is the rotational equivalent of F equals ma. Okay, and what do you do? Well, we want to solve for alpha because I am asking for the angular acceleration. And so, just rearranging this, dividing both sides by I. Tau divided by I is that 14.1 divided by 0.36, which is 39.28372. And that works out to 30, rounds off to 39.3. And the units are radians per second squared, okay? And you might look at this and you might go, okay, well, the units of I are kilogram meter squared, and the units of tau are newton meters, and where did this radians come from? Well, the truth of the matter is radians are dimensionless. They're not really a unit, okay? And that might seem confusing. You say, well, why even write it in there? Well, you're right. You don't have to. You could write per second squared like that, and that would be perfectly legitimate. The reason most textbooks and I write in the radians there is just to remind you that we're talking about rotational motion here, but really other than that, there's nothing very deep about that. Okay, so what happens is that when you work out the units here, like tau divided by I won't do that now. You actually won't get the radians. You'll actually get that. You'll actually just get per second squared. But most people will write in the radians to remind you that this is angular acceleration. Okay, so it's an angular quantity. All right. All right. Next thing. How long does it take the rod to spin up to a speed of 30 RPM? So it starts at rest. I said that up here. Or did I? Yeah, I did initially at rest. Okay. It starts at rest and it spins up to a speed of 30 revolutions per minute. How long does it take? Okay, so let's write down what we know. We know that the initial angular velocity is 0 radians per second. Okay, maybe I should just say something. When we talk about speed, you got to watch the context. So like in English, um, we're kind of ambiguous sometimes or loose with the language. So, when you say speed, you could be talking about how fast something is moving along a road. You could be talking also how fast something is spinning, okay, which is this case. I mean, you could even use speed for like how fast you download from the internet. So, the word speed in English is kind of a loose word, all right? So you say, well, what do I mean? What does speed mean in this case? And it's the speed of something which is rotating, and the speed of something which is rotating is the angular velocity. Okay, so that's the technical term, the angular velocity. How fast is this thing spinning? Well, initially it's at rest, so it's not spinning at all. After some time, and that's what we're actually working out, how long, okay, after some times it's rotating at 30 revolutions per minute. RPM just stands for revolutions per minute, so there it is. Now, we can't we shouldn't solve it in revolutions per minute. We should convert to MKS, and especially we need to convert to radians, and you'll see why radians are important here. Like you might have said, why did we work in degrees in this section? Why did we have to work in radians? And you'll see that in my next problem, okay? So you have 30 revolutions per minute, and we need to convert. So to convert the revolutions to radians, just remember that 1 revolution is 2 pi radians, okay? And so if you take revolutions in the numerator and put revolutions here in the denominator, then you'll get radians in the numerator, and this piece of the fraction here, or this piece here, will get rid of revolutions and give you radians in its place. It's also per minute, and we want to convert from minutes to seconds, so minutes in the denominator here, so put minutes in the numerator here, and 1 minute divided by 60 seconds is 1. Okay, so there's the conversion factor from minutes to seconds. You've seen this before, but it's worth repeating, and that gives you that value for the angular velocity once it's spun up to 30 RPM. That is 30 RPM in radians per second, okay? And we know that the angular velocity here is 39.28 blah, 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 blah from above, okay? That's what we calculated here. And I'm asking for the time. Okay, so if you look through those 3 equations, you realize that it's actually equation number 2 that we want, that one right there. Omega is equal to alpha t plus omega naught. Okay, so just rearranging that, first I subtracted omega naught from both sides, then I divide by alpha from both sides. That isolates t, so t is going to equal omega minus omega naught divided by alpha. Plug in the numbers from above, and I find that it only takes 0.08 seconds, so less than 1/10 of a second. So this speeds up pretty fast, okay? That's probably because I used 100 here, 100 newtons, okay? Fair size force, fair size force for a smallish rod. Okay, anyhow, so yeah, there you go. That's how long it takes for this thing to spin up to 30 RPM, okay? All right, 3 more questions here. What is the tangential velocity of either of the tips of the rod when it's spinning at 30 RPMs? So tangential velocity is actually a linear quantity. Even though this thing is going in a circle, I could still say how fast along, linearly is this thing turning, okay? And let me draw a picture because I think that'll help here. Okay, so first we're talking about an end, a tip, okay? And it doesn't matter which tip you're talking about. Let me do this, I don't know, in purple here. If you've got the colors, use them, right? So right here. So we'll just take a tip of the one of the bars there, and I just want to know how fast is this point moving, like in meters per second, linearly, in other words, okay? And that's called the tangential velocity, like that. And tangential quantities are related to their angular equivalent by formulas like this, okay? So Vt, the tangential velocity, is equal to R times omega, okay? So what's that R? And remember, R, sometimes students confuse how to measure R, but R is always measured from the point in question, or the point of interest, which, let me do it in red here, which is this point right here, okay? Actually, this point right here. That's orange, but that's okay, it'll work. All the way to the center. So you say, well, okay, how far is it from the point of interest to the center there, like that? And we already determined that that was 0.6 meters, okay? So R is 0.6, like that. And omega, well, that's the omega that we found above here, like that, okay? And r times omega will give you 1.88 meters per second. But back to like this formula here. This formula here, there's actually three of them, and they all look like this. Linear quantity, let's just say linear, is equal to r times the angular quantity, okay? So whatever the linear quantity is, whether it be the velocity or acceleration or even a length, okay, you just take the equivalent angular quantity, multiply it by r, and you get the linear quantity that corresponds to it. So omega is the angular quantity. It's how fast it's spinning in a circle. It's how fast it's rotating. You multiply that by r, and that gives you the tangential velocity. That is, how fast is this thing moving in meters per second, okay, at that particular point, at a distance r from the center, okay? So that's where this formula comes from. And above, I said that, we had to work in radians because the formulas wouldn't work. Well, these formulas, like these three, the three that we usually work with kinematics, they would actually work no matter whether you're working in radians or degrees. It's this one right here that does not work unless you're working in radians, okay? So if you were to say do this and you had, like, instead of radians per second, you had degrees per second, this formula doesn't work. Or if you had rotations per second, this formula doesn't work. This formula only works when your angular quantity is in radians, which is why in this section, unlike the rest of the course, we worked in radians. We worked in radians so that this formula here would work, and its equivalent formulas, okay? So what is the tangential velocity? Okay, well, get the tangential velocity from the angular velocity by just multiplying by r, okay? So the next question is, what is the centripetal acceleration? Now, this one is a little bit different. This one is not, you don't get that one from alpha. This one is actually you obtain from the omega, but it's, instead of r omega, it's r omega squared, okay? I'll draw a picture of it in a minute. It's actually not tangential, it's centripetal, meaning that it points towards the center, okay? So this is not responsible for getting this thing rotating faster or slower, okay? Or I guess in this case, rotating faster. This one is all about keeping, that point at the tip on a circle, okay? And so it is a center-seeking acceleration, and you calculate it as r omega squared. Actually, this we had with uniform circular motion, okay? So r omega squared gives you the centripetal acceleration, so 0.6 times the angular velocity squared, and in this case it turns out to be 5.92 meters per second squared, a little bit more than half the acceleration due to gravity, right? Acceleration due to gravity 9.8, and so this is a little bit more than that, all right? So a point on the tip of this bar would feel a centripetal acceleration, towards the center of about half of its weight, which is, significant, okay? And next, what is the tangential acceleration? So the tangential acceleration is kind of the equivalent, or the analogous acceleration to the tangential velocity. It's along the outside. I'll draw a picture showing you which direction these are in just a minute, okay? So this one, this is Vt is equal to r omega. This one is At is equal to r alpha, okay? So this is like in that series that the linear quantity is equal to r times the angular quantity, okay? So r 0.6, okay? Alpha, well, we calculated alpha above, 39.28372. Multiply them together and you get a tangential acceleration of 23.57023, or again, rounding that off the way I would on a test, it would be equal to this, meters per second squared. Okay. All right. Let me let me draw where those accelerations are, because it's a little hard to see what is what is a centripetal acceleration, what's a tangential. So let me redraw the bar here, because that other picture is getting a little bit too busy right now. Here's the center, okay? And we're looking at a point on the edge here, okay? So it doesn't matter whether it's this edge or this edge, okay? Or tip like that. There's two accelerations that that point is going to experience. There's one acceleration towards the center, okay? And this is called AC, the centripetal acceleration. Petal, in centripetal, the petal part comes from the Latin word for seek. The Latin word for seek is petere, and so this is like seeking the center. It's like towards the center. And this acceleration is just because this thing is on a circle. Okay, so you remember from uniform circular motion, you needed an acceleration whenever you're turning. And on a circle, it's like you're turning all the time. You're always turning towards the center. Okay, and so you had the centripetal acceleration, the center-seeking acceleration. But when you have generalized rotational motion, you might not only be turning, but you might be speeding up as you turn or slowing down as you turn. In this case, you're speeding up. And so you have another acceleration, which is tangential, like this. Okay, and that's AT. Okay. So a point on the tip there would actually experience two accelerations, one or two components to acceleration, one towards the center and one perpendicular, like that. Okay. Now you might say, well, there are two accelerations. Would I feel the two separately? No. I mean, if you got one acceleration one way and another component the other way, they would add, and you would say, well, how would they add? Well, they would add like vectors, right? And so, yeah, there are two accelerations, but they would add like vectors. And so your resultant vector would be something like that. That would be the acceleration that you experience. You'd experience, not only being pulled towards the middle, but also being pushed along the edge. And so ultimately you'd be experiencing a vector somewhere like middle-ish, but also edge-ish. I don't know how else to put it, but there you go, somewhere along that direction. Okay, so there you go. Those are the two accelerations that you have in generalized rotational motion. All right, let me take a look in the chat if there's any questions with that one. Excuse me. All right, I don't see any questions, so let me do the last one, okay? Well, I was going to do this one here. Let me just mention it. It's a ball of uniform mass, 3.5 kilograms, 5 centimeters, rolls downhill and drops a vertical distance of 25 centimeters. That is not how you spell vertical, okay? But you know what? It turns out, I mean, when I wrote the question, I wasn't thinking. Sorry, I'm gonna scroll that down a bit. I wasn't thinking. We actually did one like that. That was the week before the Thanksgiving break. So I don't see a point to redoing that. You could just go back and watch that live stream again. That's the reason I chose live streams over Zoom, is so that you could watch them over and over and over again. But there you go. Okay, and then I also had like a repeat, but that's okay. Let's do this last one, because this last one is a little bit more conceptually demanding. Okay, and it's a conservation of angular momentum problem. Okay, and then I think we're done. A disk has mass of 1 kilogram and radius 50 centimeters. Okay, and it's free to rotate around the middle. So you can imagine a disk, and it's got like an axis there, and this thing can rotate around the middle, and it's initially at rest. Okay. And there's a little bullet, a 5-gram bullet, and plus a little bit of an explosive on the edge of this thing. I'll draw a picture to help you think about it a little bit better. So there's this bullet and a little bit of explosives behind the bullet on the edge. When the explosives go off, the bullet is going to go flying off tangentially to the edge. Okay? Well, as you can imagine, if the bullet goes one way, the disc is going to recoil and start turning in the opposite direction. Okay? I want to know how fast is it turning in the opposite direction. All right, and so let me finish reading it, and then I'll draw a picture. It has a little bullet plus explosive on the edge. When the explosive goes off, the bullet flies off at 500 meters per second in a direction tangential to the edge of the disc. Okay, and I'll draw tangential in a minute, though I think you know what that is already. How fast is the disc spinning after the bullet is fired? Okay, so it's not spinning before and then it's spinning afterwards. Okay, so let's switch to the whiteboard, and it disappeared on me. So hold on. Here we go. Strange, sometimes when it just starts to act up, I don't know, like sometimes it just works, sometimes it does not work. Let me close this, and hopefully this is not going to crash on me now. Okay. All right, so what's the situation? So we have this disk, looking down on the disk like this. Here's the disk, and here's the middle of the disk like that. Okay, and on the edge there's this bullet. So here's the bullet, and you might imagine that like what's bracing the bullet is maybe a little tab here like this. Okay, so I know I didn't mention this in the problem, but just like imagine this little tab like this, and this tab is, well, I don't know. There we go. That tab is actually attached to the disc. Okay, and then between the tab and the bullet there like this, there's a little bit of explosive. Okay, and there's the before picture. Nothing is moving right now. Okay, the explosive goes off, and you know what's going to happen. The bullet is going to head off this way like that. Okay, and that's tangential. Okay, so like if the bullet went off like that in that direction, that's not tangential. That would be perpendicular, okay, to the disc. Okay, and or even if it went like that, that's not tangential. But going straight along the edge like that, that's called tangential. Okay, so there's the bullet, and it's of course going at five. Whoops, let me do this in blue. That's going at 500 meters per second here, like that. Well, what do you think um, the disc is going to do? So the disc, I know there's the explosives there, but the disc is kind of bracing the bullets. Kind of, when the explosives go off, the explosives are not only going to push the bullet forward, but they got to push the disc back, and so the disc is going to start rotating that way. And I want to know, how fast is it rotating? What's that angular velocity of this thing rotating in the opposite direction? Okay, and you say, geez, how in the world would I do this problem? Like how do I approach it? And it's basically a conservation of angular momentum problem. Okay, so it's kind of like the very last problem that I did in the pre-recorded lecture, where I had a bullet hitting a rod. The rod is initially standing still. The bullet hits it, and it gets embedded, and it makes the rod spin. This is the opposite of that. Instead of the bullet hitting the rod and embedding, in this case, the bullet is flying off from the disc and causing it to spin. Okay, so it's just a variation of the same kind of a theme. Okay, but it is conceptually demanding. So let's go through it. Okay, so first of all, it is a conservation of angular momentum problem. So I just wrote that, and like writing L is equal to L prime is not very illuminating. This is basically if you calculate the angular momentum before the explosion, you calculate the angular momentum after the explosion, they're the same. So this is basically conservation of angular momentum. Okay, that's part of it, but there's also kind of a gluing together of linear momentum and angular momentum. And the reason you have to glue the two together is because when you see that bullet going off at 500 meters per second right here, I mean, there's nothing angular about this, right? Like that's a pretty straight line. Okay, so that's not angular momentum there. And you go, well, how do I glue the linear momentum of the bullet to the angular momentum of the angular momentum of the disk? Okay, and so that's another kind of interesting aspect to this problem. Okay, so all right, I'm going to use conservation of angular momentum. What's the angular momentum before? Okay, and by the way, the units of angular momentum, I have them down here. Where do I have them? Might as well put them in there. Per second. Okay, they're not that interesting, but just for completeness, the units for angular momentum are kilogram meters squared per second. Okay, so what's the angular momentum before? Well, nothing is moving, and so there's no contribution to the angular momentum from either the bullet or the disc, and so the total angular momentum before is zero. Okay, what's the angular momentum after? Well, we know it's going to equal zero, but what contributes to it after? Well, the bullet's going to contribute to the angular momentum, and the disk is going to contribute to the angular momentum. Okay, so we have to calculate both of them. All right. Now, I don't know why I did the disk first, but I did. Okay, so let me just separate these out a little bit like that. Okay, so we got to look at both of these. We got to look at the angular momentum of the bullet and the angular momentum of the disk. Okay, and when we add them together, that's the total angular momentum, which we know must equal zero because it's conserved. Okay, now the next thing is, so we're looking at the angular momentum of the disk. You say, well, how do I calculate angular momentum? And the general formula is, actually, let me write it over here. The general formula is L is equal to I times omega. Okay, and you can compare that to, I'm going to put a little space in there. compare to P is equal to, oops, capital P is equal to mv, right? So what's this? This is linear momentum. So if you take the mass and you multiply by the velocity, you get the linear momentum. The angular equivalent of that is you take the moment of inertia, which is like the mass, and you multiply it by the angular velocity, which is like the linear velocity, and you get the angular momentum. Okay, so we need to add up I omega for all the pieces afterwards, and that's got to equal 0. All right, so what's the angular momentum of the disk? Well, the angular momentum of the disk is the moment of inertia of the disk multiplied by the angular velocity of the disk after. Okay, so I didn't put the little ticks here everywhere because I don't know, it would get kind of ugly. But this is all being calculated after the explosion. Okay, so you say, okay, great. Let's calculate each of these pieces um, on their own. Well, the angular velocity of the disk, there's nothing to calculate because that's what we're solving for. Okay, because I said, how fast are we spinning after the bullet is fired? Okay, so that's the angular. How fast is the disk spinning? Okay, so that's omega disk. All right, so we're not going to calculate that. I mean, sorry, we don't find a number to substitute in. We're going to calculate that. Okay, so can we calculate this though? The moment of inertia of the disk. Yeah, so it's a disk of uniform mass, so it's like 1/2 mr squared. Okay, so 1/2 m. I said what did I say? It was 1 kilogram. Yep, it's 1 kilogram. So we put in a 1 here for the mass, and the radius of this thing is 1/2 meter, 0.5 centimeters, sorry, 0.5 meters or 50 centimeters, and that turns out to be 0.125 kilogram meter squared. That's the moment of inertia of the disk. Okay, so we don't have the total angular momentum of the disk because we don't know omega, but we're solving for that. Great, that was one of these. Okay, that was this piece right here. Okay, angular momentum of the disk. What about the angular momentum of the bullet? That one's a little bit more conceptually demanding because the bullet goes off in a straight line. But you could still think of it the same way. The moment of the angular momentum of the bullet is the moment of inertia of the bullet multiplied by the angular velocity of the bullet. And at this point, you're like totally blown away because you're going, well, how can it have, if it's going in a straight line, if it's linear, how does it have a moment of inertia? And how does it have an angular velocity? So let me go back to the diagram here and let me show you how you can get both of those. Okay, it's easier to see it right now in the diagram. So, you could consider the bullet at any point here, like, there, there. Like at any one of those points, you can calculate the angular momentum of the bullet. But it's kind of hard to do it at every one of those points. The easiest place to do it is right there, just like an instant after the explosives have gone off. Okay, so that's why we're going to concentrate on this point right here, not because L is different there than it is over there. Okay, L is the same all the way along the path. It's just that it's computationally easiest to calculate it right there. Okay, all right, so let's go through it. L is going to equal I times omega. And again, this is for the bullet. So I for the bullet is 1. What? How do you calculate that? Well, it's a mass, and it's at a radius r, isn't it? Let's do it in red here. See, there's a radius r there, like that. I didn't draw this so good, but anyhow, there's your radius r, and there's a certain mass m. And so all you do is you just treat the bullet like a point mass. And what's the moment of inertia of a point mass? mr squared. Okay, and I won't substitute the numbers in here. I'll do that on the other whiteboard, but that's the formula we're going to use for the moment of inertia of the mass. Okay, and then you say, okay, well, what about the angular velocity of the bullet? Like, it's going in a straight line, so you say, well, how in the world can you relate the velocity, which is a linear quantity, to omega, which is a angular quantity? Well, listen to what I just said. How are you going to relate a linear quantity, and in fact it's a tangential velocity because the bullet goes off tangentially? How are you going to relate that to an angular quantity, and it's r, like that? So the angular and linear quantities are related by that formula, which we just used a minute ago. Okay, and so over here, now just rearranging that formula there, you can say, okay, well, it's whatever the velocity is of the bullet traveling, it's tangential like that, divided by r. Okay, and so you could see that in both cases, I'm sort of converting the linear quantity into its angular equivalent, and convert the linear quantity into its angular equivalent, and then I have that, and I can calculate that. Okay, for the bullet. All right, so let me switch back to the other whiteboard over here. And so I can say, okay, the angular momentum of the bullet, it's still I times omega. And you say, well, how do I get the angular, how do I get the moment of inertia of the bullet? Well, it's a point mass. So the moment of inertia of the bullet, I for the bullet, is just mr squared. It's a point mass. Okay, what's m? Well, m is the mass of the bullet, 5 grams. Okay, converting that to kilograms, 0.005 kilograms. Okay, and what about r? Well, r, it's at the edge of the disc. The disc has a radius of 0.5 meters, and so there's 0.5. And putting that all together, you find that the moment of inertia of the bullet is 0.00125 kilogram meters squared. Okay, and then you go, okay, well, what about the angular velocity of the bullet? And you say, okay, well, just get that from the linear by dividing by r. Okay, so you take the linear velocity, divide by r, so 500 meters per second, because I said, how fast does it travel when it flies off, when it's fired off? 500 meters per second. Okay, 500 meters per second at a radius of half a meter, 0.5 meters, and that gives you an angular velocity of 1,000 radians per second. Okay, so this idea of like converting between the linear and their angular equivalent, you could do that, and that's how you glue together linear and angular quantities. Okay, so it could get pretty crazy, but I'm not going to give you anything more demanding than something like this. Okay, so because I think this is demanding enough. Okay, great. So we got the moment of inertia, we've got the angular velocity. Put them together, I times omega here, and it turns out that the angular momentum of the bullet is going to be 1.25 kilogram meters squared per second. Okay, and so why did we do this? Well, if we go back to this one, this was the total angular momentum of the bullet plus disc after the explosion. Do we have the angular momentum of the bullet after the explosion? Yes, 1.25. Okay. Do we have the total angular momentum after? Yes, it's 0 because it was 0 before. It's got to be 0 after. It's conserved. Okay. What about the angular momentum of the disk? Well, not all of it. We have the moment of inertia of the disk, and that turned out to be right here. Moment of inertia of the disk was 0.125, so the moment of inertia of the disk was 0.125, and the angular velocity of the disk, that's what we're solving for. Okay, and so now it's just a matter of like solving, and you wind up getting that the angular velocity of the disk after the explosion is negative 10 radians per second. Okay, and so yeah, your intuition kind of fits. You expect that go back to the picture here. You expect that when the bullet goes off, when the bullet goes off, I'm running out of colors here. When the bullet goes off this way, okay, this thing is going to respond by turning that way, okay? And it recoils, in other words, it recoils, okay? And so there you go. There's an angular momentum problem, conservation of angular momentum problem, gluing together the linear momentum and the angular momentum.